Good day, folks. This is video number 16 in the playlist which deals with motion design application in 3D experience. The title of the video is Natural Frequency of a Rolling Disk, uh, Elementary Benchmark Problem in Dynamics. And this was done already in a different playlist which dealt with mechanical systems experience and mechanical system design, uh, which are different applications. So I'm repeating that in the motion design application by itself. It's a disk that is rolling on the ground and is attached on the two sides to two springs of the same stiffness. And what we like to do is the natural frequency of oscillation, if you uh, disturb the disk so that initially, for example, it has moved to the right and then let it go. Okay. Now, it's a problem that's solved in an elementary vibrations course, and it's a single degree of freedom system under certain assumptions, of course, and the analytical solution of the frequency of the vibration is given here, and the period based on the dimensions that are specified on the top is 0.123 seconds. So whatever we do, we're going to compare our result with this number, 0.123 second vibration period. The dimensions are redrawn here for your sake, and since I'm going to be using a roll curve joint between the circle on the orange piece and the line on the yellow piece, I'm going to be using roll curve joint. There is no need to specify the gravity, but in the when this was done earlier, I also did it without the roll curve joint, but there, of course, you need gravity to be active and friction to be specified, etc. And that's why it's a different problem. I'm not solving it going that route. I'm doing a roll curve joint. Here are the dimensions, and since I need to disturb this thing slightly to the right or slightly to the left and then let it go, what I need to do when I specify the free length of the spring, for example, on the left side, I'm going to assume that the free length is 0.32 meter, which means it has, in that configuration, it has already been uh, compressed. Okay, and the one on the actually this is not correct. It should be initially compressed. So this should be initially compressed, and the one on the right, I'm going to assume that the free length is 0.28 meter, which means initially it was intention. So this is not correct. Please note that in reality, if I specify these free length, the one on the left is compressed and the one on the right is actually stretched. Okay, this was a typo. Now, when it comes to specifying the mass of this cylinder, uh, if I don't specify the properties, the program itself, motion design assumes that it's made out of steel with default property in the database, which is not going to give you 10 kilogram mass. So what I'm going to do is I'm going to override the mass and make it 10. But keep in mind that when you do that, when you override the mass, these numbers, these inertial properties are not updated. And as of August of 2025, you have to input these things also. And in order to do that, I had to go to a vibration book and find out whether the mass moment of inertia about the axial direction, about transverse direction. These are the formulas. So I have to take the M and the dimensions that are M of 10 kilogram and the dimensions that I have and stick it in there. And I get 0.05 kilogram meter squared for the axial mass moment of inertia and 0.0333 kilogram meter squared for the transfers. And that's where these numbers are coming from. See, 0.05 is this number, and 0.0333 is these two are this number. So what I'm going to do initially, I'm not going to update these things. I use 10 kilogram here, but not update those. I'll show you that the answer that you're going to get is not going to be 0.0123 second period of oscillation. And then I'm going to change it so that it uses these values, and you're going to see that it's going to be very close to that 0.123 seconds target that you're going to see. And this is the other playlist that I mentioned. It deals with mechanical system experience, and I've done it twice. Uh, this is with the roll curve joint, and this one is not using the roll curve joint. And but the one that I'm going to concentrate is trying to go that route, roll curve joint. Okay. All right. Let's go ahead and do that. So we go there. We have to go to assembly design. Assembly design. Okay. And I'm going to insert my first part, which is going to be the base, that yellow piece. So insert 3D part. I'm going to call this thing base. Base and base. And since I want it to be yellow, I go to graphics and change this color to yellow. Okay, let's go ahead and make it. So on that vertical plane, I will sketch. Let me see now. I'll sketch that the boundary of that yellow piece. So probably I'm not going to draw dimensions right now. Let me just go ahead and put some random dimension here. Okay, so I'm going to use the profile to have a rough shape of that uh, yellow piece that I want. We're going to dimension it in just a minute. Okay, so first of all, I want this inside piece to be a 60 centimeter. So let me dimension this. 60 centimeter. Okay, that not centimeter. I want this thing to be 0.18 meter. Yep. Okay. Clean this up. All right. So this is 0.18 meter. This is 0.6. Very good. And let me also specify these side dimensions here. So maybe 2 centimeters there. Okay. Same thing there. 2 centimeters. Okay. Same thing down here. 2 centimeter. Excellent. Now I want this line to be sitting on there. So this line, control that line. Either you make the dimension 0 or you can say coincident. Excellent. Exit. Now we're going to pad this thing by also 10 centimeter. There we are. So we have created basically that yellow piece. Okay. All right. Now I'm going to go and insert my disk. Insert 3D property. I'm going to call this thing the disk. And since I wanted to look orange, change the color of that to orange. So let's go make it. So on that vertical plane, I will sketch. Okay, circle centered right in the middle. Okay, and let me give some dimension here. This radius is going to be 0.1 meter, which is 10 centimeter. All right, and I want this thing to be tangent to that. So this point control, this curve control that line. I'm going to go to constraints in the dialog box, and I make a tangent. There we are. Okay, exit, and we pad it by 10 centimeters. All right, I do want to create a point here on this. So while I'm in this part, disk, I'm going to say, okay, let's create a point. That's better, a lot better. Okay. So what I did a point here, I created a point here, which is 0.18 from that surface and 0.1 meter along the direction here. Okay, very good. So that's pretty much it. Now, at the end of the day, you have to create something like that. You can do it any way you want. This is the approach that I took, and let's move on. So now we're going to go to motion design right there. Oh, before I do that, I have two choices. I can make my let me go back here. I can make my constraints right now so that they become joints later on, or you can create the joints later on in motion design. I prefer to do that right now. So we're going to go all the way to the top to assembly. Let's fix that yellow piece. So fix that base. Good. And now we want to create a roll curve joint between that circle and this line. So we don't see any roll curve joints here, so you have to go to engineering connections. Engineering connections, just give it a second. Okay, and click on user define and select roll curve. See that? Where's this? Gotta find it. Roll curve right there. And it said, what are the curves? Well, there is a curve, that's the circle around that orange cylinder, and the other curve is this line. The line is the edge of that yellow piece, and then we say OK and say no. So notice that the roll curve joint has been created here, and because as it rolls, it can actually wobble back and forth, I'm going to make sure that this face remain in the same plane as that side face of the yellow piece. In other words, I want to create a planar joint. So go again, you go here, you select a planar, and we can use different ways. And for example, I use this one, plane and plane, this plane and that plane. That's to make sure that it won't wobble. And this is create a new joint. And then say okay. Notice that I have a planar joint and I have a roll curve joint. Now we're going to go to motion design. And 3D experience, or in parentheses, CATIA, that's 3D experience CATIA, of course, creates a new mechanism. Notice that, say OK, and its mechanism is created here. And you go to notice that the joints are created, roll curve joint, planar, and fixed, because they were created, engineering connection were created in assembly design that converted automatically to joints here. And there are two bodies. There is the ground that has nothing to do with me. It's automatically created. There is the base. That's the yellow piece. If you double click on it, actually, I want this thing to be rigid. It doesn't matter. I can assume it's made out of steel with this mass, etc. But since it doesn't move, it makes no difference. So it really doesn't matter whether I make this thing rigid or not. As a matter of fact, I will leave it the way it is. I will not make it rigid. I mean, you can make it rigid right there and then say okay, or you can go, you can use the properties that are given. But I made it rigid. Rigid massless. Rigid massless. That's what I mean. Massless is what I should have said, not rigid. They're all rigid. Now, if you go to the disk, double click on it, notice that it doesn't have a mass of 10 kilogram because it used default properties of steel. So now I'm going to say, okay, I want to override this thing. And I want to put a 10 kilogram here. Notice that these numbers, see these numbers here, are based on that 25.4 kilogram mass. So if I put a 10 here, it does not update those things. It does not. I will show you that this will not give me the correct answer. I'll come and change these values to the ones that I showed you in the slide and say, okay, oh, I did change the mass, but not these numbers. And it's not going to give me the right answer. So now go to machine elements, spring. For example, going between helical spring, going between this point and that point, okay? And I said that this was going to be compressed. That means the free length of it is 0.32 and stiffness of it is 6,000. Okay, good. Another one between this point and that point, and this was going to be stretched. So free length of it, I make it 0.28. Okay, and 6,000. Notice that, remember, I want to remind you that there was a typo in the slides, okay? Incorrectly, I said this is this is in compression, this is in tension, but it's the other way around. But this is good. So notice what I did. Free length of the one that is not showing is 0.32, and because at the current position is 0.3, it's already in compression, okay, etc. So we say, okay, good. It's rather unfortunate that the springs are not shown to me when they're created. Now, that's pretty much it. So, yeah. So we go to simulation. Well, first of all, let's do a preview of it, right? See that? See that? Well, the gravity is active, but it has no role. And in fact, to convince you, I go here and I say, okay, this gravity, I'm going to deactivate it. Plays no role, even if you left it active. It makes absolutely no change. Okay. All right. So here is where you can do a preview quickly to see whether it's kind of doing what it's supposed to. This is supposed to roll back and forth. Let's give it some time. It's a preview. There. Okay. So let's exit that. Now we're going to go to simulation, and here is analysis case. We're going to run it. Oh, by the way, notice that as soon as I went into motion design, a dynamic step was created for you. Double click on this thing. A couple of things. 5 seconds is a lot, so let me make this thing maybe 1 second. I'll make it 1 second. Oops. 1 second. And say okay. We're going to run it. Here's the case analysis. We're going to run it. Oh, sorry, cancel that. We're going to run it. Here's run. Wait until this finishes. It finished. Created the results. Let's go ahead and look at a few of them. Take the dynamic step. Go to the results and do a animation. Play animation. What I showed you was the preview. Was not the actual run. So okay. So this is fine. Except that what happens, let me show you something. Let me close that. And let me go ahead and do a 2D plot. What do we want? We want the disk, and we want the, for example, the angular velocity, angular velocity about the x direction plot. Notice that it's jagged, and the reason it's jagged is because of the number of data points that we asked for. So let me say okay. I'm going to go to my dynamic step here, and under setting for results option, instead of doing this, either I can make it a larger frequency, or I can go to step size and I put down every 0.01, for example, second. Give me the result every 0.01 second. Now, I didn't close this because I want to show you what happens if you ask for more steps. So let me put this thing over here. Okay, so let's go ahead and run it. So simulate, run, and look at the update. See? Right here. Good, good. Now look what happened. The period of oscillation is not really 0.123. It's around 0.15. It's around 0.15. You can see that from here to here is around 0.15. That's what the number shows there. So what I'm going to do is I'm going to say, okay, maybe I should have updated. Actually, I should have kept this thing on, but that's okay. Let's go ahead and update the inertial properties of that disk. So we go here to the disk, double click on that. This number should be 0.05. Sorry, 0.05, and these two numbers should be 0.0333, but of course it doesn't display all the digits. Same thing here. Oh, actually, maybe it does 0.0333. Okay, very good. See, these things, yeah. I don't think that's 0.0333. 0.0333. That's better. Okay, good, good. And now we're going to run it. It's finished. So let's go to the results, 2D plot, select the disk, select the angular velocity about the x direction, and look at the period now. Start at 0. Yeah, it's closer. See that? It's going to 0.117. Now, let me also show you the animation here, a couple of things about it. If you select this dynamic step, go to results and animate, and you play it, you can see that it is actually oscillating, not about the vertical line, because the equilibrium position of this thing is not the equilibrium position, the position that it started with. It's slightly to the right of it. Okay, so that's what's going on. Okay, if you can make it go faster, reset this thing. Of course, change a different. Yeah, you can fool around with the speed of the oscillation, not oscillation, the visual speed of the animation speed by choosing different numbers here. All right, folks. So that's about it. Good luck.